second speaker today will be Mr. Aditya Nandy from MIT. Aditya obtained his bachelor's degree from UC Berkeley. He then moved to MIT, and he's currently in Professor Heather Kulik's group. And today he'll be talking about some work that he has been doing on basically methane-to-methanol catalysis. Without further ado, let's move on to Aditya. So Aditya, the floor is yours.
Sounds great. Let me share my screen. 1 second here. Okay. Can people see my screen now?
Yes, go ahead. Yeah.
Okay. Hi, everybody. My name is Aditya. I work with Professor Heather Kulik at MIT. And since we had a nice talk on energy landscapes of crystal structure prediction, I'm going to shift gears a little bit and now talk about energy landscapes of catalysts. Specifically, I'm going to talk about methane to methanol catalyst design under weak thermodynamic scaling. And so every year, 135 billion cubic meters of natural gas are flared. And so that means that most of that natural gas is comprised of methane. And so we burn that methane to form CO2. So if we could instead harness that methane, which is a gas in gaseous form, and turn it into liquid form methanol, then we can harness a drastically underutilized resource. So in the realm of biology, methane monooxygenase enzymes can selectively convert methane into methanol. In the realm of synthetic inorganic chemistry, the Pareto catalyst can convert methane selectively into methanol with high 1-pass conversion and selectivity. But this occurs on a platinum core. And more recently, there's been some work done on zeolitic systems that have copper active sites in analogy to these methane monooxygenase enzymes that can also show activity for methane to methanol. And so these systems all have a couple of things in common, which is that the reactivity occurs at 1 or 2 isolated metal sites. Many of them have 3D transition metals, and they also face the same challenges. So they need to be simultaneously selective, active, and stable to be practically usable. And because many of them have 3D transition metals, they can frequently contain open shell electron configurations, which means that they will have unpaired electrons that must be accounted for. And so I was interested in seeing whether we could use transition metal complexes to tune the energy landscape for methane to methanol to improve catalyst design. So transition metal complexes are of particular interest because the design space of ligands is very large, and by changing out the ligand, we can change the properties of the transition metal complex. And so to quickly discuss methane to methanol itself, the mechanism that is typically assumed for this reaction is the radical rebound mechanism. So throughout the rest of my talk, I will be using this mechanism. And so when we have the radical rebound mechanism, we start with a resting state catalyst. In this case, we'll consider mid-row transition metals ranging from chromium, manganese, iron, and cobalt in oxidation states 2 or 3. So in the first step of this landscape, we form a high-valent oxo intermediate in the oxo formation step, usually using a 2-electron oxidant such as nitrous oxide. After we form the high-valent oxo species, that high-valent oxo species can pull a hydrogen atom off of methane to form this hydroxyl species, and then we're left over with a methyl radical that can then recombine with the hydroxyl species. So the pulling off of the hydrogen atom is known as the hydrogen atom transfer step here, or HAT. And then when we're left with the methyl radical, that methyl radical can then recombine with the hydroxyl species to form the methanol on the catalyst in the rebound step. And then that methanol can be desorbed from the catalyst to return it to its resting state in the methanol release step. So I want to quickly highlight that all the calculations that I will show in this talk today are DFT calculations performed with this functional and basis set combination. But when we consider the full energy landscape of methane to methanol, it's important to consider the fact that we want a catalyst that can not only activate methane, which is a challenge, but it also needs to be able to release methanol. And so because many of these 3D transition metal complexes can have unpaired electron configurations, the first thing we set out to do was to evaluate whether spin state influences catalysis and how we can incorporate the role of spin and oxidation state to design an optimal catalyst with the best trade-offs between these multiple objectives. And so the first question we set out to answer was, does spin state actually matter for reaction energetics? So if we take a look at the first two reaction energies of the methane oxidation energy landscape, which are commonly studied in the literature, and we color here just oxidation state 2 compounds, we color them by spin state. Just from the histograms alone, we can see that there's clear clustering by the spin state. So if I take a look at oxoformation energy here on the left, we're going from lower d electron count to higher d electron count. So as we go from chromium to cobalt, the metal oxos become more unstable, but we see clear groupings here by low spin, intermediate spin, and high spin. And so we see a counter observation when we look at hydrogen atom transfer, but it's not as direct. So here we can see with oxoformation, it uniformly becomes more unfavorable with higher D count, but we see this boomerang shape for hydrogen atom transfer. So this motivated us to look at the coupled reaction energies to take a look at this energy landscape. So what I'm showing here is a kernel density estimate. So there are many different ligands sampled in this energy landscape that I'm showing here. But we see that we would not be able to draw one line through all of this data. And so if we did that, we would have something like this, but then whole clusters of, for instance, the iron or cobalt data would not be well described by the single linear free energy relationship. And so if we take a look at the explicit scatter here, it recapitulates the picture that we see in the 1D histograms. I will focus here on iron, which is on the bottom left. And so we can see on the iron energy landscape, there is clear grouping by spin state. For example, the dark circles are low spin iron 2 compounds, whereas the squares and triangles, the dark squares and triangles, are intermediate spin and high spin iron 2 compounds, and they lie on completely separate lines. So the lesson this teaches us is that we would not be able to use a single linear free energy relationship for catalyst screening across all of the data with different spin and oxidation states. And to really emphasize this point, the next thing we will do is compare the linear free energy relationships on subsets of spin and oxidation states to the linear free energy relationships present in the literature. And so what I'm doing on this plot is showing the slope on the y-axis of the lines fit through the plots that I was showing on the prior slide. And so in the literature, for the OXO and the HAT linear free energy relationship, many examples have been reported, and the tan line shows the slope that's been reported there. Our fit through all of the data is shown in the blue line. And so now if I first plot only oxidation state 2 compounds, we see that there's, again, large variation within each spin state. And even accounting for fit errors, we see that individual spin states do not match the literature data. This picture is emphasized even further when we consider both oxidation state 2 and 3 compounds. So the general conclusion that we can get from this is that even if we take a look at just one metal, the variation in spin and oxidation state has a stronger influence on the linear free energy relationship. And so we must be considerate of that when we perform screening. And so just looking at the OXO and the HAT steps is insufficient. And so again, the goal we set out to achieve was that we wanted a catalyst that can activate the CH bond of methane, but also release methanol and not be poisoned. And so to consider that, we would have to consider these two steps of the reaction energy landscape, where we have hydrogen atom transfer shown here and methanol release. And so if we took a look at the relationship between these two steps, we see that that assumption of linearity just breaks down even further. So we see a huge amount of scatter. The argument of fitting one line through all the data breaks down even further here. But for an optimal catalyst, we would want to design something that activates methane, so has more favorable CH activation thermodynamics, so to the left of this plot, but also releases methanol easily, so down to the bottom of the plot. So what this means is that we want to find compounds that are more down towards the bottom left for improved catalyst design. And to do this, we have to introduce new chemistry beyond what already exists, so that we can sift through a large space and see if we can find any counterexamples that lie in this region. And so to do this, we constructed design space of compounds, and we take experimentally known compounds and break them into fragments and bridges that we recombine. So I'll show an example of what this means. So here we have fragments of commonly studied macrocycles, and I can take bridges and stitch them together. So for instance, a combination of fragments and bridges here creates this macrocycle, which we can then coordinate to a metal and screen for catalyst design. So this is just one example of a macrocycle that we can coordinate to our metal, but we need to combine this with some axial ligands as well, and some metals. So here I will just narrow down and focus only on manganese and iron due to the spin and oxidation state variation. And so together, these make a very large set of 16 million transition metal complexes. So these are what these resting states look like for these transition metal complexes. And what we want to do is screen them for methane oxidation. And so when we have 16 million transition metal complexes, it's not easy for us to readily screen all of these with something like density functional theory, which would take way too long for this whole set of compounds. And so we are interested in screening using this type of methodology because this strategy recovers existing chemistry while introducing new chemistry. So the example I'll give you is if we take pyrrole fragments and stitch them together with methylene bridges, we can recreate porphyrins, for example, which are commonly studied in the experimental literature. So next, I want to show the strategy that we took to actually perform our screening. And that strategy is called the 2D expected improvement method. And so again, I want to highlight our goal here, which is that the catalyst should activate the CH bond of methane, but release methanol. And so we have our 16 million compound design space, which is very large. And so we won't be able to perform density functional theory calculations on all of them. So we use k-medioid sampling methods to narrow down the design space to a more tractable number, and we can perform simulations on those compounds. So each dot here represents one potential catalyst, and what I'm showing here on the X and the Y axis are the computed hydrogen atom transfer and methanol release energies. Now, we want to get information on the full 16 million compound space, and we can't do this easily with DFT. So what we do is we take the DFT data that we have, we fingerprint the transition metal complexes with a cheap fingerprint. Here we use a graph-based fingerprint, and then we train neural networks based on the DFT data to independently predict the hydrogen atom transfer energy and the methanol release energy. After we have the neural networks, we can make a prediction over the full design space. And that's what this looks like. So this is all 16 million compounds as predicted by our neural networks now. And what I'm coloring them by is a score that we can assign each compound using this 2D expected improvement method. So what this gives us is the balanced trade-off between exploration and exploitation, and tells us what we can do to potentially expand this Pareto front, which I've shown in red. So this is one generation of this process. So after we score the catalysts, we can take the best cases, and then we can repeat this procedure in the next generation. So we select those compounds, perform the DFT calculations, retrain the models, and then repeat this procedure. And we can see that we have expanded our Pareto front and found at least one example that has better hydrogen atom transfer and methanol release energetics. So we can continue this process to an arbitrary number of generations. So I'm going to show 3 generations here. And throughout this process of evolving this catalyst energy landscape, we can actually find compounds that exist optimally on the Pareto front. And at the same time, this active learning procedure improves our models. And so I want to highlight that in the initial generation of our search, we don't find any of the Pareto optimal catalysts that we find at the end of our search. Most of them are found in the last generation. And so we can take a look at kind of what are the chemistries that are picked out at the end of our search. And we see that low spin iron 2 compounds, primarily with oxygen coordinating ligands, are selected, along with negatively charged axial ligands. And so negatively charged strong field axial ligands. We can also now have the improved model, so we can see why things are on the Pareto front. And so when we take our models over the full 16 million compound design space and take the best 30,000 candidate catalysts, we see that there's a strong selection for negatively charged axial ligands. And then if we go try to explain this by using the DFT data that we gathered, we can try to understand why this happens. This was a surprising find because none of the best-in-class catalysts for methane oxidation have axially charged anionic ligands. So we actually found that the reason why this anionic axial ligand is beneficial is that it makes the metal less electropositive and has methanol bound less tightly because of it. And so this gives us a tangible insight that we can actually gain from this data. And so the same analysis here I'm showing with Mulliken charges, but it holds with Hirschfeld charges as well. And with that, I'd like to just conclude my work here that has found that there's strong spin and oxidation state dependence in linear free energy relationships. So we cannot readily use these linear tools that have been applied for catalyst screening. And we can use machine learning to discover unintuitive catalysts that have Pareto optimal trade-offs between reaction energetics and then try to understand why they occur. And with that, I'd like to thank everybody for their time, specifically Professor Haji Akbar and Sarupriya for inviting me to give this seminar, and the Kulik Group and funding for supporting this work. Thank you.
Thanks, Aditya, for the wonderful talk. So let's give Aditya a round of applause. And we can now move on. We have time for a few questions. So if there are any questions, just raise your hand and we can basically, okay. Or you can write it in the chat as well. So I have a very naive question about these DFT calculations. I know that DFT methods are really accurate in some systems, but have issues in some other circumstances, like let's say dealing with water. So to what extent are these observations agreeing with experiments? Have you tried to test, or do you have experimental collaborators who can make and test some of these structures?
Yeah, so we have not extensively undergone collaborations with experimentalists as of yet, because this work actually was just recently published. However, we have done extensive studies. I was looking for the backup slide, but I don't think I have it here. We have done extensive studies on DFT functional dependence to all conclusions, for instance, in this work. So in transition metal chemistry, for instance, there's strong dependence on the amount of Hartree-Fock exchange that's used in a global hybrid functional. And what that functional is can influence each step of the reaction energy differently. And so we actually have found that the trends in our data are fairly functional agnostic. However, so the rankings of catalysts can be fairly functional agnostic. But there are certain types of spin and oxidation states where we have increased sensitivity.
Okay, thank you. So any other questions from the audience? Okay, if not, we can probably give both of our speakers another round of applause and thank them for the wonderful talks. So thanks everybody also for attending. This will be the end of the official part of today's event. I will stop recording right now. Feel free to hang out, however, if you want to basically talk to the speakers, or if you want to network and connect. So, and we'll see you in 3 weeks.